Hello everyone, am I audible? Hello, am I audible to all of you? Somebody can unmute and speak. Oh yes, okay, good. And I believe you can also see me. Yes or no?
Yes, sir. No, sir. You're not visible, but audible, sir.
Oh, I'm not visible.
Now visible, sir.
Okay, good. So welcome to this live session. And before I begin, I just want to know what is your impression on the course before we go into the technical questions? Any general feedback? Is it like tough or is it like anything that you want to share?
Good evening, sir.
Yes.
I'm Subramanian, doing PhD in MIT Chennai. And this course is really awesome, sir. Really challenging. It is not easy for me, but it is very challenging. Every week, I'm doing assignments regularly and I'm trying to score 100. And every week, I'm scoring 90 and not getting 100. I'm totally engaged in this course and I'm learning. Although I'm working in CFD for more than 5 years now, I got to learn a lot of new things in this course, and I'm following this course very well. This is about the general things. I'm really liking this course and learning a lot from this course. Thank you, sir.
Thank you. That's very encouraging. Yeah, I mean, I understand. So the turbulence itself is a tough subject, and there is also an absence of comprehensive material. I mean, you will see in some textbook you will have some theory, but not on the modeling. Even if it's modeling, you will see only certain type of, let's say, only the eddy viscosity models. It will not have large eddy simulations or so on. So a comprehensive material itself is not so much available, in my opinion. So therefore, there will be. I understand it will be challenging, and it's good that you felt it was useful. Anybody else
Yes.
want? Or if you have any questions, also please share. I'll be happy to answer.
Yes, sir. I have one question,
Yeah.
but actually I'm outside, so if there is some other noise in the call, I'm sorry for that. My question is, I am working in combustion flows, sir. So in trapped vortex combustion, internal flows, I have done lots of CFD in that. I'll directly come to the question, sir. So I have a bluff body inside the combustion chamber and a cavity. So currently I'm using SST K omega models, and I'm doing reactive flow, non-reactive flow, steady and steady flows, and all those stuff. My doubt is, so far, this Prandtl number, and I am choosing only the SSTK omega model. I'm not playing with the, I'm not modifying the constants in the equations. So for capturing the effects of wake behind the bluff body on the flow, what should I do related to the solver constants?
Okay, understood. So can you please tell me, is it subsonic combustion or is it going in transonic?
Yes, subsonic combustion, 40 meters per second velocity. Only thing different from pipe flow is we have two bluff body inside the combiner.
But what is the Mach number?
40 meters per second, so it is very, very low subsonic, 0.002, something like that it will come.
Okay. So one thing to clarify is all the methods that has been discussed in this entire course.
Yes.
I have taught mainly for incompressible flows, but the same models are also used without any, let's say, any corrections or any other changes, even to subsonic flows. So if you do a subsonic combustion, it's straightforward to use all the methods that I have taught in the course. Only those who are doing transonic supersonic flows, the same models will have certain correction terms, because let's say there is a shock coming in into the flow. then of course, for that, the numerical methods will also change. The way you discretize and solve the equations will change. And also the models require certain small corrections. Let's say there is in epsilon equation, one extra dilatation term is added. These kind of things, small changes will be there. Otherwise, the course is as generic as possible. So coming to specifically to your question, you're using k omega SST and you're saying to predict the flow separation, what you can do
Yes,
better.
sir.
One thing I can tell you. So see, the flow separation itself is even if you remove flow separation, we see that there is an anisotropy in the even a pipe or a channel, right?
Yes.
So and this anisotropy is even pronounced. Let's say when you have this a black body inside the chamber, so you have a flow separation and everything. So having an eddy viscosity based model, it will do only as much as it is capable of. So if I have to restart it, let's say if I was you and I have to do this from the very beginning, I would pick detached eddy simulations.
Okay.
Okay. Are you using a particular solver or is it in-house code you're writing?
No, sir. ANSYS Fluent only I'm using. I'm not writing any code.
Yeah. So ANSYS Fluent has an option called delayed detached eddy simulation, DDE.
Yes, sir. Yes, sir. I know. Yes, sir. It is.
Yes, I think I have mentioned in the course, but it will come. I mean, we have not completed the course, right? So
it is coming on 10th week or 11th week, I guess, sir.
This will
I've seen
come-
the syllabus.
yeah, this will come later. So I would recommend you to use that one because it is only a little bit more expensive than your RANS calculations. But it's at least you will get a lot better results because some parts of the flow is resolved or captured rather than modeling. And it is almost like it is a hybrid method. So it's like it will recover the RANs in certain zones and it will go to LES in certain zones. So I would say if you can afford, if you have a computer that can detect
Yes, sir. Yes, sir.
Now we can speak.
am I audible? Hello? Am I audible to you all? I briefly lost internet connection.
Now it is okay, sir.
Yeah, you can also see me, right?
Yes, sir. Visible, sir.
Okay, excellent.
Good. You can share also.
Yeah.
You
What
need
is
to
it?
write. You need to write anything.
No.
Okay.
It's fine. Yes, sorry about the interruption. There was a
Yes,
network
sir.
issue. Okay, so what I was telling is that in the absence of the validation data, you at least do a sensitivity study. You click on another model.
Okay.
go back and see whether you're just the K omega or a RNG K epsilon, any
Yeah,
other.
realizable epsilon I'm doing. For sensitivity, SST and realizable I have done, sir, so far.
Yeah, you can do that in the absence of the any validation data. You are
Validation, we have say experimental data only for non-reactive flows.
okay. Yeah, so I would not recommend coming to your last question. I would not recommend changing the model constants because these constants have been tuned to generally work, in general to work for many types of flows. So there is some kind of a reason behind why these constants were chosen. But if your Fluent guide, user guide, does it say if it says you can tune it, and if they have a reference for it, you can go ahead and do that.
Okay, sir. Okay, sir. Thank you, sir.
You're welcome. Any other questions from others? Are others very shy to ask, or they have no questions? I see if you have joined. This is basically a Q&A session. So there is
Hello,
there'll
sir.
be nothing like I'll write and start lecturing. This is all done already.
Sir, can I ask one more question related to exam? Hello, sir.
Am I audible again? Hello?
Yes, sir.
Hello? Yeah, I'm audible. Okay. There was again some internet issues. Okay. Any other questions?
Sir, one question related to exam, sir.
Okay.
Sir, how many questions will be there in the final exam? Sorry, sir.
Okay.
I'm just curious to know how difficult will it be? Will it be in the same level of difficulty like your assignment exams? Will it be more difficult?
You can tell me what you like.
So whatever it is, I'll prepare. But just asking, just wondering, because will you ask derivation or something to spend more time question like that, or questions like assignments?
Yeah, it will be an MCQ based. The pen and paper is. I'm right now not feeling to have a pen and paper type of an exam.
Okay, sir.
Mainly because it's there is a lot of students I have to sit and evaluate for this. And yeah, if it's very less students, you can do this. So when I teach this course here, we sometimes do a project-based evaluation also. Unfortunately, that is again very difficult with 60, 70 students taking. Each project is very difficult to evaluate. Sit here and watch for your presentation what you did. So it will be similar to the assignment with with some surprises here and there.
Okay, sir. I'll prepare accordingly. Okay, sir. Thank you.
Yes.
Sir, while you are discussing some of that assumptions or not assumptions, and while doing the modeling, taking some experimental data from your work area or some other papers. So we are considering that into our models. So how is it will be? We don't know that previously how we did the experiment, right?
I did not get your complete question. Can you say it again?
Yes. Sir, sometimes you bring that your experimental data, like plot budgeting of URMS, like that experimental data. You'll show that this is this value. You said that experiment some values we take. How to say, right? C mu value like C epsilon 1, like that values you are giving from the experimental data, and we are substituting again in the equations what we are getting. That is experimental data. We don't know how we got, right? I mean, on what basis previously their experimental data came into picture?
Which one? The data that, like, while deriving CMU or this other model?
Yes, sir. Experimental data, right now I'm seeing into the K epsilon equation only right now. I'm just
Yes.
telling as an example, sir. Like you are saying
And
sometimes you're taking the experimental data itself in considering doing some modeling, some experimental like values to get some other C epsilon 1 or C epsilon 2, what we will get.
correct.
Without knowing, right now I want to do some modeling. Actually, I don't know how to do modeling of this. I don't know previously when I didn't come to this course, what is like a background work of these things, how it will work. Now, after coming to this course, I learned this, that, oh, this is the background, how it will work, why this is, models are very good. Then after you were saying that while coming towards this last seventh week lectures, that you are doing that C epsilon 1 or epsilon 2, C epsilon 2, that you took some experimental data plus 1.25 plus or minus 0.06 that you took from the experimental data itself. So we are doing it in a modeling way. Normally, we don't know experimentally because we are deriving a simulation way. Normally, we are constructing a simulation based work. So
Correct.
we don't know previously the experimental work, how it will be a very, I mean, how you will say that this will be a very good approach.
I never said this is a very good approach, right? So the objective of this course is to tell you how these models work, and these models are all available in the domain. It's there in the commercial solvers like Fluent, CFX, or even in OpenFOAM. It is
Yes,
also
sir.
use it in solvers. So the objective of the course is to tell the theory behind this model, how these models are constructed, what assumptions have gone into it, so that when you use this model for a, let's say, as Subramanian said, is a combustor. I have not taken a combustor example, right? So he is trying to use a model which is built for, let's say, flat plate boundary layer non-reactive flow, and he is using it in his combustor, and he is saying the results may be good, may not be good. That is the purpose of the course, to so that you are aware of what are the assumptions are there, so that you can make a guess how good these results will be.
Yes.
That is, in the absence of any reference data or experiments data, whatever new simulation you are going to produce, that is your data, right?
Yes.
So how much you will believe in it. So let's take an example of a case where you cannot do experiments. For example, weather forecasting. This I told in the class itself, right?
Yes.
So you can never measure tomorrow's weather, right? And the weather, every day you'll get a weather report, how it is tomorrow or even 1 week ahead. Sometimes you'll get long-term predictions, 1 month also. And if you see, they will put an error uncertainty in their predictions. So it is a prediction. How much you want to believe depends on how many assumptions are there and how good or bad assumptions it has gone into. So if you don't want to use such methods, then the next part of the course will handle the eddy resolved methods. That is where you can avoid using such, what to say, very industrial models or such kind of crude approximations, and go into resolve the flow, and results will be more acceptable.
Accurate. Yes.
Yeah, but it will come at a cost. These simulations will be expensive.
Right now, this many of these machine learning models are came into picture. As of that these decades, these people, our researchers are also using this machine learning approaches for these numericals also. Right. It become in mechanical engineering, these governing equations are also again well establishing now again. So will it be like again it will impact this back? I mean, impact this back means any accuracy will be there like that if the increases like if the users.
Yeah, I mean, for example, one can revisit to look at, so what they have done to establish this model constants is some kind of a data analysis only. So it's not like one particular flat plate boundary layer data is taken and then they have made that model constant. They have looked at in general whatever data was available at that time, and the model constant, some approximation was done at that time, part of time. So now one can revisit with more data available. You can use your machine learning algorithms or any other optimization algorithms to see whether you can get some other model constant. But just by predicting a better model constant does not mean that the RANS models will suddenly start to predict everything about turbulence. For example, the anisotropic nature of it. Because no matter what model constant you are using, you are still solving turbulence using a scalar quantity called turbulence kinetic energy, or a dissipation rate of kinetic energy epsilon or omega, right? You are not seeing the turbulence as an anisotropic process. And so that and that will actually have an impact on the accuracy of your results.
Yes.
So just by tuning constants will not get you great results. So in that aspect, you can see most of the models that is being used. You can see the references, whatever I've taught. These are all the standard models available in the commercial solvers and open source codes, and they're all not now. You hardly see anybody saying that there is a new k epsilon model and the constants are like this. People have stopped looking into from that perspective, like changing constants and then give a new name. Let's say I change C mu C epsilon 1 and I will call it Vagesh K epsilon model instead of RNG or something. That is no longer acceptable. Nobody will use it.
Sir, yes, you mentioned that it should be universally I mean, if I design a model or if I put a model in front of this modeling community, that should be acceptable for the universal flows. I mean, universally, it should be applicable for all type of flows.
So what I mean there is that the model, when you construct the model, there are many things to look at, not just the accuracy. Accuracy is one aspect. The other aspect is whether this model will work for different types of flows.
Yes.
Let's say there is a standard K epsilon model.
Yes.
This will work for atmospheric boundary layer flow, weather forecasting. It will also work for combustion. It will work for blood flow. It will work. It has been proven to be numerically robust.
Yes.
So the code will not crash, right? So if models are constructed such that equations becomes very stiff, so numerically it will lead to convergence issues, and the code can crash. So then people will use that models less. For example, the K epsilon V2F model or the V2F class of models, it was popular at some point of time. Today, not many people use it because it has issues with numerical stability. The code will crash or it is very difficult to get the code started. So if you construct a model, what I meant was it should be working for many types of flows, not just for, let's say, pipe flow or flow over a circular cylinder or something. But you should not expect it to give good results in every flow. That depends on your model assumption, right? If you're making eddy viscosity type of an assumption, Bussinesque, obviously you're compromising on lot of accuracy issues.
Yes, sir. Understood.
Yeah.
So that is what, sir. After your classes only, I know that what is going on background. Previously, I don't know. I know only the models how it will. I know the models. This is for this will be there. So if I want to combine this both k omega and k epsilon, I mean that one is near to the wall, it is very good. One is away from the wall, it is good. As yesterday, these lectures you spoke about this in this last lectures.
Yeah.
Yes. So
Yes.
some people will be like, if you are said that in that example, you said combustion, you want both in near the wall aspect, you want both combustions in the engine. In that type of one example, we need both because as of that piston will go away from that TDC. So the amount of flame, how much it is burnt or the soot will come, whatever it is that inside the mixture, we want to know everything what it is happening inside. So in that type of case, what should we will use that model, which both are one is for one thing and another is for another thing. So what will be the use here? Which model we can use?
No, I told you, right? You have that the first student here, I think Subramanian, he has already told the K omega SST. That has an automatic blending. So if you use K omega SST, it recovers omega behavior close to the wall, and it recovers K epsilon behavior away from the wall. So you choose K omega SST instead of K omega or K epsilon separately.
Yeah, like a jet impingement, sir. Right now, I will ask just one question. That is jet impingement technology. Right now, jet impingement. Right now, they are using in this electronic cooling also. Okay, so it will the jet will impinge upon the cold plate, right? Here also, should I use a transition SST or K omega SST?
The transition SST, if you have to go and see the theory behind it, if they have developed that model for a transitional flow, that is, if the flow is going from a laminar to a turbulent state,
Yes.
if you have that kind of a flow, or if you have a relaminarization, the turbulence is dying down to a laminar state, maybe in that kind of a thing, they have done some correction to account for it. So first you have to see whether in your impingement zone or the oncoming jet itself is laminar or turbulent, you need to see. If its oncoming flow is already turbulent and you expect the downstream flow to be turbulent, then a realizable constraint will or should handle your impingement zone alone. That I think I've talked in detail what happens at the impinging zone.
Yes.
That the models go unphysical, and therefore you need realizability constraints or use a realizable models. That should handle. But if your oncoming flow is laminar and downstream it is becoming turbulent,
Yes.
then maybe you would need the transition based
Yes, sir.
K omega.
Yes, sir. You said that one time in the example that free shear boundary layer.
Mhm.
Boundary free shear stress shear force. It is that you said in a topic called free shear boundary layer in the in the near the jets, where it will my inlet of that velocity, it comes the Reynolds is around laminar only. But if it comes into that impinging into the another fluid or the same fluid with different velocities, then it is a turbulent, sir. Whether it is a
Can you
turbulent or not.
repeat your problem?
Sir, right now in the jet impingement case only, sir, what you said, free shear boundary layer, you said a topic called free shear boundary layer.
Oh, yeah. Okay.
Yes. In that free
Yes.
shear boundary layer, the velocity, two different velocities, the fluid with two different velocities means the impinging part, the impinging from the fluid coming from the orifice is impinging into the fluid in the downstream, right? So the both are of different velocities. Maybe it is in the different velocity and different direction, and it is coming from that vertical direction towards this. So the inlet velocity is the inlet is laminar. Then after impinging, will it may turns into turbulent?
It's possible. It's possible.
So
Like, for example, the wake is a very good example for this. If you look into any wake flow, your oncoming flow can be still laminar, but
yes, sir.
downstream of bluff body, you can get turbulence.
Yeah.
Because of the shear that is encountered downstream from the flow separation, you have a low speed flow in the flow separated part, but above that you have a high speed flow. So the friction between the high speed and low speed, especially the reverse flow, right?
Yes.
When you have a separation, you have a flow reversal.
Yes.
So low speed flow going against the high speed flow, causing additional shear, can break down into turbulence. And this happens in wakes, where downstream the bluff body, you will see turbulence, but upstream you will not see any turbulence. So it can happen like that.
Then we
A
can
flow
use a
can basically have multiple regimes. It need not be fully turbulent. It can have some zones laminar, some transitional, and some turbulent. It can be like that.
Understood, sir. Sir, the most
Then you
of
have to be careful here, especially with when you're using RANS models, because RANS models are assuming that your entire flow system is turbulent.
RANS model is always assumes that it will be turbulent. If we are using
If your entire flow system, it will assume that it is turbulent, because it's a turbulence model, right? You're modeling the
yes.
flow system as turbulent, so it assumes this is a turbulent system.
When there is a laminar flow in that one, will it resolve that one? It not will it not, right?
You may as I said, it's very difficult to predict and say what will happen there. But um, yeah, in general, you can get, that's what I said, like this impinging zone where it should get least amount of turbulence. But since it is based on the strain rate, it is predicting opposite.
Yes.
So it's becoming unphysical. It is a laminar zone with no turbulence, but it is predicting high turbulence. So you can get kind of unphysical things when you use RANs in such problems.
Sir,
So I would recommend to use eddy resolved methods. This will start, I think it will start next week or so. You can see the syllabus. So that part, both the large eddy simulations and the hybrid methods that have occurred in the next part. They are better.
For a cost, it comes for a cost, right? But it is very high computational cost it require, right?
No, today detached eddy simulations can be done. I think depending on your flow problem, I think it can be done on a decent workstation. It doesn't require a large cluster. The whole point of this hybrid method, so you need to wait for the entire course to finish. Then only that hybrid methods will come.
Yes,
Uh,
yes.
so I think after this, I think the direct numerical simulation is not done yet, right?
Yeah, not done.
Yeah. So that is the fully eddy resolved method, you can say, like zero turbulence modeling.
Yeah.
So, but that is very expensive. That is what I do in my lab. That is the research we do, but that requires a large supercluster or a supercomputer, which is in general it is not used in industrial flows. One, it takes the time and also the resource. But there are methods like somewhere in between, a compromise between the computational time and giving you reasonable accuracy.
Yes, understood.
Yeah, but
Excuse me, sir.
very large scale problems, you still have to use RANs. For example, the weather forecasting, it is still a RANs based calculations. That's why there is a lot of uncertainty. You will see that they will say like monsoon this year is going to be above normal by 10%. And they will say monsoon will arrive on June 1st. But if it doesn't arrive, they say it's delayed by 1 week, right? So
Yes,
because the model has so many assumptions.
Yes, sir, understood. Sir, how this cyclone?
Hello. Hello. I think Professor has disconnected.
I think sir have some connection issues, I think.
Yeah, he got disconnected.
Yeah, that's okay. Okay, bro. Thank you. Bye-bye.
All right.
Hello? Am I audible?
Yes, sir, you're audible now.
Yeah. Sorry, we lost the internet again. I believe I'm visible to you again.
Yes, sir, your video is visible.
Yes, yes. So there is some internet issues, something beyond my control. Yes, there is some turbulence also in the internet. Okay. So any other
Sir,
question?
I have one question, sir. In week 7 when we were discussing about week 6 when you were discussing about K epsilon, then you said that realizable K epsilon has something called as realizability constraint, but then you did not discuss about what is unrealizable there. So what exactly is unrealizable, like realizable? What is that in the K epsilon model?
In the K epsilon model.
Sir, yes, sir. When you were discussing about standard K epsilon, and when it ended, that time you said that there is something called as realizability constraint, and later you did not discuss about that. So, what exactly is realizability constraint?
Did I cover this already, or it is yet to come?
No, sir. In week 6, you in the end of this RNG K epsilon model,
Okay.
then that time you just highlighted this, and later on. Okay.
That means it is there's a separate chapter on it. It will come. It is if it has not come yet, it is going to come. This entire the full series of lecture I have already recorded last semester when I gave this live to the. I mean, I taught it to my students and it was recorded simultaneously. That's why you will see that there is sometimes there is some disruption. Some student is asking question and maybe questions are not audible and so on.
But sir, next week is about boundary condition, and we have already completed K omega. So next week is about boundary condition and initial condition and damping function. So realizability is not in the list of the syllabus that is provided on the web page. So
I have already recorded. I have thought it will come. The entire realizability constraint is going into more than a few hours of lectures. It will come. If you have not seen already, it is going to come.
okay, sir. Okay, thank you. I wanted to ask about wall model alias. Sir, like wall modeling in RANS, we had this. We were doing this wall functions, and we are putting the wall functions according to the shear stress at the that P point of the cell in the inertial layer. And sir, is wall model alias also the same thing? Does it do the same thing?
Yeah. So this is covered when I go to LES. So you're asking these questions a little earlier, but so in the LES also, if you are resolving the viscous sublayer, or if you are modeling it, the same approach is used. Like if you are going to use a wall function based approach, they will also have a near wall modeling based LES. They call it WM LES, wall modeled LES.
Okay, sir, got it.
Yeah. This will come. All these questions, your questions will come because you are ahead of time. We have to finish realizability and all this and finish the RANS part. Then it will go into the other eddy resolved and all this.
Good evening, sir.
Yes. Please, Shankar, please tell me. You are muted. Am I audible?
Good evening, sir.
Yeah, please.
Yes, sir. Yes, sir. It is audible, sir.
Yeah.
Good evening, sir. Thank you for teaching the course. It is very interesting, even though it is derivative. I'm working on gas turbine combustion, sir. I'm doing PhD full time at MIT. I'm going to start my research. Just now I have completed my coursework. My problem statement is that I'm going to work on fuel injector, which is for gaseous fuel, such as which is for methane to high hydrogen fuels. I'm planning to design a burner, sir, which is of fuel stabilized combustor type, where I have an axial swirler and then I have an injector for gaseous fuel. even though I have a little bit knowledge about using models in solver, I don't have any knowledge about coding. This course is very useful so that I can understand what are the terms which are present inside the solver, and what are those contribution in solving those behavior, fluid flow behavior in the problem. It is very useful for me, sir. Can you suggest me to start with? I'm going to start CFD simulation by using commercial software such as ANSYS Brilliant. Can you suggest can you suggest me any good model for my problem, sir?
That is the whole purpose. I should ask you this question. After you complete this course, you should be able to tell. That is the objective that I have told in the very first class itself. What is the objective of this course? The outcome. The outcome is that you should be able to decide, I will take this model to solve this problem. That is left to you actually, because I should not be able to decide before knowing the problem. Because you're telling me in generic, in area, gas turbine, right? Within that, there are different issues, different flow problems. Is it like based on cooling? Is it based on is it in the compressor, or is it in the combustion chamber? So the problem statement changes. So which model is used is very difficult to predict without knowing the particular problem. That's why rather than doing that will happen like more like consultancy. For example, instead of teaching this course, I can just say I'm a turbulence modeling consultant. You can come here and ask me questions, show your problem, and I will tell you go and use K epsilon. And then Subramaniam will come and I will tell use K omega SST. Then of course, where is the knowledge transfer, right? I'm not transferring any knowledge to you. I'm just telling you use this model. And you will probably never ask any questions. You will say, yes, Professor Vagesh is saying, so I will use it. So that is completely not the purpose of this course. The purpose is that so that you should be able to decide for yourself what is the best one. Okay, does it satisfy your question, Shankar? Am I audible to you, or are you muted, or?
Yes, sir, you are audible.
Yes, sir, you are audible, sir.
Okay.
Okay,
Sir, I want
thank you,
to
sir.
ask something.
Yes, please.
Somewhere I have seen that there is unsteady runs and steady runs. I want to hear about something about that. What's the difference about those two?
Okay, so this is just a terminology. So when we say RANS, the RANS equations already has an unsteady term, right? It's a dou by dou t, unsteady rate of change of your any property is already there. So this is just a like a historical basis. So many decades ago, doing computations were tough even on a computer. Even RANS calculations were computationally expensive, right? Many, like 30, 40 years back or 50 years back. So then they started to do steady calculation. They would drop the unsteady term, and then they will calculate only the steady state flow equation using CFD techniques. And they started to call it RAN solution. But later in time, when computers were slightly getting better, then they included the unsteady term. Then they started to call it unsteady RANs. You understand what I'm saying? This is just with the time it has happened, but I don't think we have to care so much about it, because whatever I've thought, it has the full model equation, the unsteady term is there. So whether you want to, so whatever I've thought is unsteady RANs for you actually.
Okay, thank you, sir.
Yeah, so that is just a history problem. There is nothing special there. Unsteady, the RANs is nothing but unsteady RANs. Any other question?
Sir, there is also different schemes that FEM, FDM. So which one we should focus on in CFD?
Okay, you're asking the question on the how to discretize these equations or models that is thought. and take it into an algebraic form. Because right now the equations are in continuous form, like partial differential equations. So take continuous to algebraic form. You can use any method that you are familiar with. These models are not built for a specific discretization method. You can do finite volume, finite difference, or finite element. In general, I can say that finite volume is more popular. And that's the reason for that is it uses what is called, if you have already taken a CFD course, you would know that a finite volume method, you start with conservative form of the equation. So you can write a governing equation, a general transport equation in terms of what is called non-conservative form or a conservative form of the equation. And when you write the equation in conservative form and discretize and use it, this method is finite volume. And when you do this, your results at any given time iteration, or especially when you are iterating it, as the simulation is going, the results are conserving the mass, momentum, energy properties, unlike finite difference or finite element. So finite volume therefore became very popular in fluid mechanics, and all the commercial solvers, at least the popular ones like ANSYS Fluent, ANSYS CFX, and other codes, even open source codes like OpenFOAM, they're all finite volume based. For this particular reason that the solutions are conserving mass, momentum, energy, or anything, any property that you're solving at all times, at all intermediate times or time steps, not just at the end.
So for complex geometries, which one is better?
Again, that has nothing to do with both finite difference, finite volume can be done. That is not a problem. Finite element.
Okay, sir.
That is not a problem, whether it's complex geometry or simple geometry. It is not based on that. The decision is based on the solutions that you are going to solve. Do you want it to be conserving your mass, momentum, energy, or you want to have some errors? That is the idea there. Any other question?
Sir, I have one question regarding the Bosnius approximation. You said that that UI prime UJ prime is the eddy viscosity multiplied by strain rate tensor. Now, and minus 2/3 k of delta Ij. The delta Ij part I could understand as to why there was 2/3 k delta Ij. But when we look at this, so you gave the example of plane Couette flow. That in plane Couette flow, that strain rate tensor, that in a fully developed condition and in a homogeneous setup, it becomes zero. So that part, so that 2/3 part actually conserves the kinetic energy. Now, what I wanted to ask is that how are we sure that that UI prime UJ prime is not depending upon the higher orders of Sij? So we had Sij, standard tensor, but how can we make sure that it is not depending upon the higher orders of del UI by del xj? So why isn't there a del UI by del xj a higher order of that? I mean,
okay, yes. If I understand correctly, you're saying we are using we are modeling it based on the stress relating to strain. Why are you not using something like a second order derivative terms?
sir, like higher power, like not. Why is there non-linear terms are not there? So in both, uh, so like there are only linear terms in a sense. Del UI by del xj, linear part only. So there, why isn't there del UI by del xj square?
Whole square.
Yeah, whole square.
See, yeah, as I said, you need to look into the dimensional form also. Right, you can model it. As I said, there is no limit for modeling here. One can construct it. First thing is, even when you solve the Rance equation, you have a nonlinear term in the advection part or the convection part, right? So you get your, let's say, dou by dou x of uu in the left-hand side of the equation, Rance equation. So you get a u square term. Whenever you get a u square, the nonlinear part, that is the challenging part in analytical solutions, is not possible for a nonlinear PDE. And even in a CFD calculation, if you have taken a CFD course, it would have been taught how to linearize that equation, how to linearize the term. So there is a way to linearize that part. So a nonlinear term always puts up a challenge, even in the CFD framework, but there are techniques to linearize those terms and solve. So if you want to put a higher order term, first of all, you need to justify taking it to another dimension, whether that becomes strain or is it like, what is it? You need to give an explanation for it. You can construct the model, but as long as you can bring it into a dimensional form where it looks like a strain, it's fair enough. And if you are able to get converge solutions for it, that means numerical stability, it's also fair enough. So you can actually think on those lines also. It's unnecessarily getting complicated because you are changing the nature of the strain and the dimensions to something else. And then you need to bring back the dimensional correctness by adding some other term so that dimensions becomes correct. And then you have to have and then you have introduced a nonlinear term. You need to linearize it while solving it.
Sir, I was just thinking from the mathematical perspective because UI prime, user prime, these correlations are themselves non-linear. And when we try to model, so they are turbulent quantities. Now we are trying to model it using the mean flow quantities, and those mean flow quantities are also themselves taking the. So that is why, like, so I cannot.
Interesting, a very interesting thought, and perhaps people have already tried it. I don't. My research area is not on RANs, so I know the methodology, and I don't do any research in this area. So perhaps somebody must have thought about it, and maybe there is something called nonlinear eddy viscosity models. It somehow didn't become very popular because of the numerical stability issue, where eddy viscosity expressions were based on some nonlinear, as you said, some higher or introducing some higher order terms and so on. So a nonlinear eddy viscosity model also exists. It's just that people have stopped using it. So as I said, you can build your knowledge. Once you complete this course, you can always easily look into it and see the pros and cons of those models, why it was stopped, why people are worrying less about those models. It's an interesting thought, I agree. You can, since the stress has a nonlinear term, why not the strain will also have it? It's a good idea.
Okay, sir, thank you.
Now, the objective of this course is, as I said, it's one, as I told Subramanian and others, that you should be able to choose a model based, since you know the theory. The second thing is you should also able to make your own model. That is even better. So yeah, I'm really glad that you guys are thinking actually on those lines. I'm really happy for knowing about this.
There is one thing, sir, I want to highlight that one person from our research group was he wrote K epsilon and K omega model, and that time K epsilon model did not. We were validating over this plane quote flow, and we had this flat grid and smooth, smooth flat grid, and that time K epsilon model gave errors. So it was, and K omega model on the on the same way of discretization, it gave on the same schemes of discretization and finite volume, it gave the answer, and that time we were confused. And after watching the lectures, when we saw that you have changed that production term, which was containing epsilon, to some to a other term, in explaining that, that there will be numerical stability issues. When we look back into our code, we realized that we had actually discretized it in the original form of K epsilon.
Okay.
That
decoupling the production term.
Yes, sir. Yes, sir. That was that. Even in code, we have still this date today in his thesis. I read that and I informed this again. So we are looking back at the code and trying to change it now.
Nice. And where do you work now?
Sir, I am at IAC. So I yes, sir. I gave the interview actually in IIT Madras. You took the interview at that time.
In what department?
Yes, sir, in applied mechanics.
Okay. And you got the admission?
Yes, sir. I got an IAC also in IIT Madras also.
Okay.
So I joined IAC.
Yeah. Okay.
Can I show you the picture if it's okay?
Yeah, you can. Yes.
Can I share my screen?
Yeah, if it's possible for you, if you have an option, you can.
Is it visible?
Yeah, I can see your screen.
Sir, this is the K omega model, and we were trying to validate this part. Can you see? So this was the K omega model, and sir here, and this was the K epsilon model, and K epsilon model got we were not able to figure it out also why it was like this. So this is K epsilon, and this result is of K omega. So there was the K omega gave us happy results. So we went on with this.
Okay, so it is not the model but the implementation.
Implementation problem, yes, sir. Yeah.
Good. Any other question? No, I think we have done 1 hour, but yeah, if you have any last question, I can take it up. And I intend to do this more often. So is this time preferable? This is good for everyone?
Yes, sir.
Okay, so we'll continue with this 5 to 6. I think I've been told that this will also be recorded and posted on YouTube. So for those who couldn't join, or if you want to see it for yourself. So yeah, and I look forward to meet you again. Any last question if you have, I can take it up.
Sir, one question regarding tensors. As to, can you give a reference for where to study tensors from? Not from too much mathematical perspective, but we can prove the identities. That's that much.
I personally use incompressible flow by R.L. Panton. There's a textbook. It's a fluid mechanics textbook for postgraduate students, like master's, PhD students. Ronald L. Panton, R.L. Panton. So that has one chapter. So it is, as I said, it's not like, it's light. It's not like a mathematics book, and it's nicely explained. You can read that.
Okay, sir. Thank you. Thank you.
Yes. Okay then. So I'm happy to meet you all, and let's look forward to another session later as you move into eddy resolved simulations. Okay. See you all, and best wishes and good luck to your research studies. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.